Okay, so our last but not the least keynote talk is by two folks from Open Networking Foundation, and they are going to talk about the deeply programmable 5G edge cloud fabric, and it will be given by Sunay and Carmelo Cascone. Oz is the VP of R&D for mobility at Open Networking Foundation. He leads all the mobility projects at ONF, including Ether, that some of you might have heard about already. And before that, he was at Argela, USA, where he was the chief technology officer. He has done some very pioneering work with bringing software-defined networking to RAN, especially for RAN slicing. He has had a career in industry and academia before that. So that is Oz. He will be joined by Carmelo, who is also at Open Networking Foundation. He leads our programmable data plane team and is applying that programmable data plane solutions to many of ONF platforms and solutions, including the BNG, the 5G user plane, and so on. He is a PhD from Political di Milano, and he got that in 2017. So with that, Oz, do you want to get us started?
Yes, thank you, Guru. All right. Hello, everybody. So today, together with my colleague Carmelo, we will talk about how we are realizing a programmable 5G edge cloud fabric with P4 at ONF. So our talk is about building a programmable 5G edge cloud fabric. So I thought it would be a good idea to do some level setting and start with an overview of mobile networks in general and how they are being transformed with 5G. So at a very high level, mobile networks are composed of two distinct parts. The radio access network, or the RAN, enables wireless connectivity to terminals that are potentially on the move. And RAN also ensures efficient use of wireless resources while fulfilling quality of service requirements. The mobile core network, on the other hand, provides IP connectivity sessions to mobile terminals for both data and voice services. It also controls these sessions to ensure that they are not interrupted due to mobility. They fulfill certain quality of service and subscriber policy requirements. Unlike prior generations, 5G is different. And the biggest change it brings is the revolution in how we operationalize mobile networks. And this transformational change starts with disaggregation and virtualization of the network functions on the path towards cloudification. In the RAN, this plays out by first disaggregating the base station into a number of components and virtualizing the ones that mainly conduct packet processing. In the core, the disaggregation gives us user plane, control plane separation, followed by functional disaggregation of the control plane. Today, all of these components are virtualized and increasingly containerized. And the second step is SDNization. In the RAN, most of the mobile link control is lifted from the disaggregated RAN components and are realized as a suite of applications running on a RAN-optimized SDN controller. And in the core, the SDNization involves P4. Since the user plane component conducts packet forwarding and processing operations, it is possible to realize it on a programmable forwarding element, such as a Tofino fabric, with an associated SDN control application and a microservice that is responsible from interfacing this user plane with the 5G control plane in a 3GPP standards compliant way. And this is how we get to start building a programmable 5G edge cloud fabric. I mentioned that 5G is different because it is effectively leading an operational transformation. 5G is also different because it will have to serve many diverse use cases. And one very important use case will be towards enterprises. Enterprises are bringing automation to their processes with Industry 4.0 transformation. And for this, they see 5G as a very critical enabler. This means that in addition to the traditional nationwide deployments, 5G will bring about a very large number of localized private network deployments. And at ONF, we have been developing Ether, a managed 4G, 5G edge cloud platform for this market. Ether is a programmable platform, top-down and end-to-end. The programmability starts with the programmable 4G, 5G fabric, and of course extends to the mobile core, and also includes the RAN. And the end-to-end programmability is overseen by Ether's runtime operational control component, the ROC. And programmability brings fine-grained telemetry, verification, and closed-loop control capabilities to Ether. And with these capabilities, Ether is now resilient against software and hardware failures, network congestion, and various types of attacks. And the programmability also allows us to operationalize and run Ether in an automated way using CI/CD and GitOps principles. And last but not least, we are on our way to extending the closed-loop control capabilities towards external edge applications. So you have already heard about this from Jen. Just a year ago, along with Stanford, Princeton, and Cornell, we were awarded a DARPA project we call Pronto. The collaborative goal in Pronto is to realize the 5G network as a programmable platform and bring verification and closed-loop control to it, and also operationalize it and take it all the way to pre-production. And Ether is the foundational connectivity platform for Pronto. So now let us see how Ether and Pronto architectures look like. Ether is built on a P4 programmable fabric composed of Tofino switches today, with a roadmap to include programmable NICs in the near future. Ether uses programmable 5G small cells that are Open RAN compliant. The fabric control plane is the highly available ONOS with control applications for IP forwarding, INT, and 5G core user plane. This user plane is developed in P4, and you will hear a lot more about this from Carmelo in a few minutes. Similarly, the RAN control is the microservices-based cloud-native ONOS optimized for RAN control. And naturally, the edge cloud also hosts edge applications. And in the case of enterprises, most likely these edge applications enable automation for manufacturing, machinery, and processes with 5G connected devices. But going back to our fabric, we have the INT collection along with verification and closed-loop control platforms around this telemetry. And note that now that we have the 4G, 5G core user plane realized in P4, the INT is giving us telemetry data for the 4G, 5G traffic as well. So verification and closed-loop control solutions around 5G connectivity are now possible with Ether and Pronto, of course. And together with the edge cloud and container management platform, this is what we have at each Ether edge. Running centrally, we have the mobile core control plane, as well as the overall management platform for Ether that handles hybrid cloud management, runtime operational control, monitoring, logging, alerts, as well as automated CI/CD and GitOps processes. And the central units have the capability to oversee many, many edges. And Ether has been operational for the last 18 months. We have over 10 edge sites with a fair number of new sites in the pipeline. The pilot network uses the free general authorized access in the CBRS spectrum, and its central components run on Google Cloud today. One of these sites happens to be the Stanford Flight Lab, home to one of our Pronto partners, Professor Max Schwager and his team. They are conducting some pretty exciting research on how to get drones to autonomously and collaboratively fly tight formations. And for this purpose, we deployed Ether with a small cell and furnished all the drones with CBRS dongles so that they can communicate with each other and with the drone control applications. And these applications also take input from the infrared cameras distributed in the flight lab. And this setup hosted some pretty amazing verification and closed loop control demonstrations on the programmable 4G, 5G fabric, all outputs of the Pronto team. We showed how the programmable fabric gives you resiliency against network congestion due to microbursts, resiliency against denial of service attacks and exfiltration attacks. We also demonstrated how programmability gives us operational automation and how we can use it to rapidly recover from hardware and software failures. I will include the links to some pretty exciting videos of these demonstrations in the deck that we will share with the audience. So now let us hear from Carmelo on how we use P4 to specify, architect, and realize the 4G, 5G mobile core UPF to enable our first version of the programmable fabric for Ether.
Thanks, Oz. Everyone, I'm glad to be here. As Oz mentioned, I'm going to use the rest of the time to talk about how we design our P4-based UPF, its unique benefits, and some of the challenges. So I'll start by saying that we use a hybrid software-hardware architecture. At the center of everything, we have our switch, which is based on Intel Tofino that provides connectivity between base stations, some compute nodes, and the internet. We use Kubernetes to run cloud-native edge applications, and because of their proximity to the base station, this allows to provide, again, very low latency services. In this architecture, we actually find two kinds of UPF, a software-based one and a hardware-based one. The software-based UPF runs as a container on Kubernetes, and this allows us to essentially achieve horizontal scalability. We can easily spin up new instances for scalability, but also for isolation. However, dedicating CPU resources for such a function is not always the most cost-effective option. For this reason, what we can do in Ether is to actually offload some of the sessions into the switch. So what we have essentially is a second UPF. This time is hardware-based. It's realized in P4 and runs as part of the switch pipeline that differently from the software-based UPF is able to provide very high throughput in the order of like terabits per second, ultra low latency, less than few microseconds, and with very predictable low jitter in the order of nanoseconds. This UPF is not a full-blown UPF. I would say it's a minimal UPF that works well for enterprise and IoT use cases. So we provide a number of features from 4G and 5G compliant GTPU termination to slicing in QoS to usage reporting and idle mode buffering. But this UPF is not provided as a standalone feature. Instead, as Oz mentioned, it's part of our ONF SD Fabric solution. And as part of SD Fabric, we support deployments of different sizes and redundancy requirements. So from a single switch deployment to pair switches for high availability, as well as leaf spine topologies for multi-rack deployments. The important thing here is that the UPF, even in multi-switch topology, the UPF doesn't run on just one switch, but instead we treat the whole network as one big UPF, and we abstract it in this way to the 5G core control plane. The other important thing is that, again, a programmable data plane opens up infinite opportunities in terms of visibility, and in general, like features that go well beyond that of a traditional UPF. So what we did is we started by implementing support for in-band network telemetry. So today we have INT well integrated with the UPF function, and this allows us to essentially monitor flows from mobile devices. We're able to look inside GTP tunnels and generate INT reports for those packets, and so be able to track things like path, latency, or detect anomalies like packet drops, etc. And as Oz mentioned, this visibility capability are being explored more also as part of the Pronto project. And so as part of Pronto, we also had some of the universities integrate more advanced fine-grained measurements algorithm in this pipeline. And we already heard how this opens up to the possibility of implementing closed loop control. We actually saw a demo in the first keynote from Nate on Tuesday. So I'm not going to spend a lot of time on these features. Instead, I want to talk about another important feature that we are working on. It's currently in the roadmap for 2021, and which is end-to-end slicing in QoS. There were some questions in the keynote yesterday as the Fabric keynote, so I decided to add one slide about slicing. So I'll try to explain what the problem is and the challenge here we're facing. So the idea of slicing is that of taking a physical infrastructure and sharing that between independent logical networks. In our case, this infrastructure is made of 3 stages. We have the radio access network, we have the fabric with our one big UPF, and finally we have our compute resources and internet access. The desire is to be able to partition this physical infrastructure into slices. A slice is essentially an independent, again, logical network with security and isolation guarantees. And the idea here is that we want to be able to create slices targeting potentially different services and different QoS requirements. So what do I mean by that? When we talk about isolation, then the simplest example is that where devices of a slice should not be able to communicate with other slices. At the same time, the traffic of a slice should not affect the perceived performance of a different slice. So there should not be interference in terms of perceived bandwidth, latency, jitter, packet drops, etc. When it comes to QoS, then the idea is that each slice might have different QoS requirements. In this example, we have slice A with 2 different QoS classes, a low priority one and higher priority one. But a slice designer, which is usually in our case would be the edge app developer, might decide to create a slice with only 1 QoS class or more, depending on the type of applications that they're trying to run on this slice. So how do we realize this? Well, there are several techniques to allow this sharing of the physical infrastructure. And in our case, I want to just focus on the fabric. So when it comes to implement slicing, it's all about using things like ACL rules, rate limiting, or using schedulers serving either shared or dedicated queues. It's also about routing, for example, the idea of like using dedicated paths for certain slices. So the problem here is to be able to provide slicing together with this isolation, security, and QoS guarantees in a scalable and cost-efficient manner. So for example, we could allocate different slices into different switch queues, but usually switches have a fixed number of queues. And in the case of data center switches, like those that we use in SD Fabric, this number is pretty small. So in order to scale up the number of slices, we will have to share queues between slices. So what are the implications of sharing queues? Can there be interference between slices? The answer is likely yes. So how can we limit this interference? And this is one of the challenges we are currently facing and working on to solve. And actually working on this as a roadmap item for 2021. So next, I want to focus on the control plane architecture. And now we leverage P4 to provide integration with the 5G control plane using what we call the virtual P4 defined reference UPF. To explain that, let me start from the bottom. So we use white box switches running Stratum, which are controlled by our Oguz SDN controller using P4 and time in GNMI. On top of Oguz, we have different applications controlling different aspects of the network. And one of these applications is actually in charge of abstracting the whole topology as one big switch, which happens to be P4 defined. So the idea is that the 5G core control plane thinks that the whole network is actually a one switch implementing the UPF function. And this allows us to scale up the underlying topology independently of the 5G core control plane. So this virtual switch abstraction is realized in the most natural way possible, which is we use P4. So in this architecture, we actually have two P4 programs. We have our program that we compile and run on Tofino. This is called Fari.p4. This program defines tables for UPF, routing, ECMP, etc. And it's highly optimized for Tofino. Then we have our reference UPF P4 program that it's much simpler than Fabric in the sense that its implementation is not optimized for any hardware target. Instead, we try to define what I call database-like tables. This P4 program doesn't run on any switch, but is instead used as a data model for the runtime API between the 5G core control plane and the SDN controller. Actually, it's not just used as a data model for the API, but we realized that using P4 really made an improvement in our development process, because P4 today is used as the lingua franca between different development teams inside the ONF. So when we started working on this UPF implementation about a year ago, we took this document from 3GPP called the PFCP specification, which is actually a specification of the protocol between the control plane and the user plane in a mobile network. This specification actually defines a forwarding model using the match action abstraction. It is actually inspired by OpenFlow, but it does so in a very ambiguous way. This forwarding model is specified using the English language and figures. So what we did is we started meeting the mobile core team and the Fabric team to discuss the features we wanted to implement, and to be able to agree on how to realize those features and how to be able to control them at runtime. What we start doing is writing P4 code, and that's how we have this reference UPF P4 program. To be able to agree on how to control these features at runtime, we write PTF test. So we went from an ambiguous specification to running code as a formal contract, not just between software systems like control plane and data plane, but also between development teams. And this allows us to work independently. So we have on one side the mobile core team working on their pieces of the implementation, so the mobile core control plane, and which they are able to test and validate using the BMV2 software switch simulator running the reference P4 program. On the other end, we have the Fabric team that works on their pieces, which is the Tofino P4 program and the UPF application running on top of ONOS, which we can then validate using the same reference test that we defined before. And this really made an improvement in our development processes. But I want to stress on this point a bit more. And I want to mention about the opportunity to unlock true control plane portability, not just for the UPF, but also for other telco appliances. Today, we realize our hardware-based UPF using switches. But the idea is that out there are many data plane targets that we would like to consume, from SmartNICs, FPGA, to software-based targets like eBPF, DPDK, etc. The problem here is that we can program these targets to provide equivalent forwarding behaviors, but we will end up with pipelines that look slightly different, because each pipeline tries to optimize the underlying architecture of each target. And to be able to actually have control plane portability on this target is usually quite expensive. So the idea is that we could have a reference P4 program, our reference UPF P4 program, and be able to write our control plane once and be able to run this control plane on all possible targets, because the control plane would only talk against the reference UPF P4 program, and then we could have this P4 runtime translation layer that takes care of like mapping P4 runtime requests from the reference pipeline to the target one. And there have been important advancements in the industry and academia that could really make this a reality. So the first one is from Google, P4 Workshop 2018. If we were to manually implement this P4 and time translation layer, Google showed how today they use P4 to enable automated switch validation of their fixed function switches. The idea is the same. How can we get that confidence to be able to deploy a new target in our network without having it break in production? So the idea is that we can use P4 program analysis, in this case of the reference P4 program, to do FADS testing and do in general this automated test validation that could help us validate all these different targets. But there's also another opportunity of being able to automatically generate this P4 and time translation layer. There's a paper in SDI 2021 that describes how, given to P4 program, an abstract one and target one, the translation logic between the two can be synthesized. So what I'm trying to say here is really a call for operators, vendors, and standard bodies. If you truly believe in disaggregation and the benefits of interoperability, then we should really consider using P4 as part of our specification process, not just for UPF, but also for other telco appliances like the RAN, at least certain components of the RAN, BNGs, OLTs, etc., because this could unlock what I call control plane portability. So to conclude, there are some benefits. There are a lot of benefits of using P4 for the implementation of UPF. There's an obvious one, which is we are able to realize a high performance UPF that allows us to free up CPU resources. But there's also an unexpected benefit, which is P4 really improved the control plane development process and interoperability. And what I'm talking about is this idea of working on a reference UPF program. We are facing some challenges, which mean research opportunities. So I invite everyone to come talk to us. I talked about the slicing problem. I talked about the automated validation of new targets. There's also another problem about being able to dynamically allocate sessions between the hardware and software UPF. Today it's a static allocation, but there are opportunities to make this dynamic. And finally, looking forward, I already mentioned this. Today we run this hardware UPF on switches, but we want to be able to do the same using SmartNICs and FPGAs to use that on deployments without a top of rack switch. So for all the SmartNICs vendors out there, if you're interested in collaborating, please talk to us. And finally, we're also looking at extending the P4 programmability all the way into the RAN, or at least some components of the RAN, like the centralized unit, to be able to achieve this better end-to-end visibility and closed loop control. And this is the end of the presentation. Thank you.
So thank you, Oz and Carmelo. Great presentation as always. So a quick question that is, let me take it from the audience, and that is, how are you combining fabric.p4 and UPF.p4 into a single implementation?
Well, today is a manual process. So we manually work on one P4 program that combines both routing functions, UPF functions, and INT, etc. It will be nice for us to be able to independently work on different P4 programs and then use compiler toolchain to stitch them together in the most possible optimized way. But we're not there yet. So today it's a manual process.
Okay, so Oz, I have a question for you, or Carmelo and Oz, both of you. That is, when it comes to RAN and ORAN, how far do you think we can take P4 and programmable data plane into RAN, especially if we were to take ORAN architecture as an example? So how far can we take it into CU, DU, RU, and both the control plane and the user plane of these functions?
So in the ORAN architecture, let's look at first the overall RAN stack that is distributed between CU, DU, and RU. So that is a combination of packet processing and signal processing functions. So the components that mainly look at packet processing are in the CU. But having said that, those packet processing functions involve header compression, and encryption. So we have to be able to find ways of realizing that in P4. And that may require some P4 extensions. But at the same time, also, if we want to bring in INT to the CU, that effectively means, again, also expanding the idea of INT, because effectively, the minute your IP packet goes into the CU, it is no longer an IP packet. You turn it into progressively move from IP packet to physical layer packets. And then that also has the added complexity that if you want to do an end-to-end verification or closed-loop control, then you have to realize that the packets within the RAN are going to have different headers, RAN-specific headers that will be appended to the compressed IP header, and you will have to map that into the IP packets so that you know exactly that those are the same packets that we're dealing with. So those are the kinds of challenges that we are going to have to face. But having said that, I think in the CU domain, some level of P4 and some level of INT should be possible. And then for the rest of the RAN, the kind of telemetry that we will collect is going to come from the RAN optimized SDN controller and the kind of telemetry application that will instruct the RU and the DU to provide information about the links, the mobile links.
Okay. So obviously you are the Mr. RAN slicing. So I have to ask you this question about RAN slicing in a public forum. That is, can you say something about what does 3GPP specify in terms of standard for RAN slicing? Then what is current state of the art for RAN slicing, and how would you then differentiate the ONF proposed RAN slicing against some of the current state of the art?
So 3GPP leaves RAN slicing to implementation. So there is no specification. So it defines slicing IDs and leaves it at that. And how you implement it in the RAN has not been standard. There is, to my knowledge, in the coming releases, there is no explicit desire to do it either. So that is going to be where vendors differentiate themselves from one another. Now, as far as the state of the art is concerned, one of the earliest RAN slicing POCs, as you know, we have done at ONF using Oguz, and that was in 2016, if I'm not mistaken. And since then, the only other company that has started claiming being able to do RAN slicing has been Ericsson, and they've announced that only this year. So that's where things are. From a slicing perspective, I think the ONF proposal is I would say the most comprehensive one, and it is combining the ideas or bringing the ideas of SDN and cloud concepts into the RAN to enable RAN slicing. So effectively borrowing from cloud, we define in the RAN space resources, and we exactly like container management systems work. We can dynamically or statically pin the resources, spectrum resources, and using SDN do that programmatically.
Okay, very good. So I guess my last couple of questions, and then we should move on. That is, Carmelo, you mentioned something about this single switch abstraction for the fabric in order to enable the kind of the control plane to work on it and do some of the checking and all of that. How easy is to generalize that for other class of application? So is it only in the context of UPF, or can it be done for other kinds of applications running on the top as well?
Sorry, running on what? I missed the last bit.
So that it can, for other applications, also you can generalize this concept of a single switch that can be running on a fabric, or it can be running on different types of infrastructure.
Yeah, well, for UPF, it's pretty easy because a UPF is essentially a specialized router with a bit more QoS. And so everything that looks like a router, it's easy to specify in P4s, and there are not big challenges in then mapping this one big abstraction to a topology. In the case of our fabric, we use MPLS segment routing inside the fabric. So the idea is that the UPF function is really mostly applied at the edge of the fabric, so in the leaf switches. So we transform the packets there, and then we use segment routing to move packets from one leaf to another. And we could easily apply this approach to other functions as well. So I said the UPF is a specialized router for mobile network. Another example of specialized router is a BNG for fixed network. We could easily use the same approach. And there are other telco appliances. I haven't done much work to see how easy it would be to specify them in P4. But for example, if you take the OLT at ONF, we did this work on Volta where we abstracted the OLT using OpenFlow. Actually, not just the OLT, but the whole PON network. In our work, we mostly focus on a topology with a single OLT and one switch aggregation. But the idea is that that processing could be abstracted again using a single switch abstraction. So using a P4 program like the virtual UPF, and then we could easily scale up and down the topology that we use to realize the residential access, like in the case of Volta.
Okay, very good. I think we are running over time, so I want to bring that to close. So I want to again thank all our keynote speaker pair, Jen, Anya, Oz, and Carmelo, and all the audience for your participation and all the questions that you contributed. And with that, I want to hand it over to Denise for some of the closing logistics that she wants to talk about.